Nothing about this valley in western Serbia looks unusual, yet beneath it sits a mineral that almost perfectly matches a substance invented for a comic book. Not metaphorically, not loosely, but chemically. Long before anyone thought about lithium batteries or geopolitics, Superman's writers accidentally described a compound that Earth would later produce exactly once. That coincidence is where the story of jadarite begins. Jadarite does not announce itself in the field. It is white, earthy, and dull, forming massive beds rather than showy crystals. There are no glowing shards, no dramatic veins, no visual clues that something extraordinary is present. For years it sat unnoticed in drill core from the Jadar Basin, dismissed as another bland industrial mineral until detailed analysis revealed a chemical formula that made mineralogists stop and check their notes twice. Lithium, sodium, silicon, boron, oxygen and hydroxide, arranged in a structure unlike anything previously known. A mineral species new to science, quietly waiting in Miocene lake sediments. The scale mismatch is part of what makes jadarite unsettling. On the surface, the Jadar Basin is a modest lacustrine depression formed during the Miocene, filled with carbonates, clays and evaporitic sediments. In the subsurface, it hosts one of the largest known lithium-boron resources on Earth, locked not in brines or hard rock pegmatites, but in a mineral that should not, statistically speaking, exist at all. Jadarite is not just rare in quantity, it is rare in concept. Very few people realise that jadarite is still known from only one natural locality on Earth. 2 decades after its discovery, no other basin, no matter how lithium-rich or boron-rich, has produced it. This is not because geologists haven't looked. It is because jadarite sits at the intersection of chemical conditions that almost never overlap in nature. To understand why, you have to understand the basin that made it. The Jadar Basin formed as part of a broader system of neogene extensional basins across the western Balkans. These basins were influenced by post-orogenic collapse, crustal thinning, and lingering heat from earlier magmatism. That heat matters. Jadarite does not form at surface conditions. It forms deep in sediment piles, under temperatures approaching 200 degrees Celsius, long after deposition has finished and long before metamorphism begins. This is a narrow geological window most basins never pass through. The lake that once occupied the Jadar Basin was alkaline, saline, and unusually enriched in boron and lithium. Boron likely entered the system through volcanic ash and hydrothermal fluids linked to nearby granitic intrusions, while lithium was concentrated by prolonged evaporation and recycling within the basin. Many basins have one of these ingredients. Almost none of them have all of them at once. As sediments accumulated, early minerals crystallized first. Carbonates dropped out, then clays, then common borates. Normally, this is where the story ends. Lithium gets scavenged by clays, boron forms simpler borates, and the system chemically exhausts itself. In Jadar, that did not happen. Instead, lithium remained mobile, silica stayed available, and boron concentrations remained high, deep into burial. Jadarite formed during high-temperature diagenesis, not at the surface and not during metamorphism. It crystallized from alkaline brines migrating through compacted sediments, assembling a structure that includes both triangular and tetrahedral boron groups. Lithium in tetrahedral coordination, sodium in distorted octahedra, and hydroxyl bonded into the lattice. This mixed coordination is inherently unstable in most environments. It requires precise pH, temperature, and chemical balance to persist. Laboratory synthesis has confirmed just how restrictive these conditions are. Jadarite can be made artificially, but only within a narrow temperature range of roughly 180 to 230 degrees Celsius, at moderate to high pH, and in lithium-boron silica systems that closely resemble deep alkaline brines. Even then, synthesis is inconsistent. Slight deviations produce entirely different minerals. Nature does not like jadarite. It tolerates it only briefly, under rare circumstances. This is why jadarite remains a type locality mineral. It is not just rare because it's only been found once. It's rare because it requires a geological accident layered on top of another accident, timed perfectly, and then preserved without later overprinting destroying it. Most basins cool too fast, others alter too extensively. Many never concentrate lithium and boron together in the first place. The mineralogy itself reflects this instability. Jadarite crystals are microscopic, rarely exceeding a few microns. They grow as massive aggregates rather than discrete forms, suggesting rapid nucleation and limited growth before conditions changed. Associated minerals like silicium, analcime, and albite record an alkaline, sodium-rich environment that was constantly flirting with different crystallization pathways. Jadarite is the outcome of one very specific path winning briefly, then freezing in place. Then there is the composition that made jadarite famous. In Superman lore, Kryptonite was described as a sodium, lithium-boron silicate with hydroxide. When jadarite's formula was published, mineralogists realized the fictional writers had accidentally described a plausible mineral. The match is not exact, but it is close enough to be uncanny. A made-up alien weakness turned out to be chemically sensible, and Earth had quietly produced its own version. The resemblance ends there. Jadarite does not glow, it does not emit radiation, it does not weaken superheroes. What it does contain is lithium in concentrations that matter enormously to modern society. In that sense, meaning rather than mythology is where the comparison becomes uncomfortable. Jadarite is valuable, not because it is fictional, but because it sits at the heart of the energy transition. What makes this more interesting is that jadarite represents a lithium pathway completely different from the two dominant models. It is neither pegmatitic hard rock nor evaporative brine. It is a sedimentary diagenic lithium mineral formed after deposition, under heat, in a closed chemical system. That means it points to an exploration model that geologists are only just beginning to take seriously. Yet despite this, jadarite has not appeared elsewhere. Western Anatolia has borate-rich basins, South America has lithium brines, China has alkaline lake systems. None have produced jadarite. The reason appears to be timing. Either lithium is locked away too early, boron precipitates first, or burial temperatures never reached the narrow window required. Jadarite is not just rare in space, it is rare in time. This also explains why jadarite tends to occur deep in a sedimentary pile, rather than near the surface. By the time conditions are right, the basin is already buried. By the time uplift exposes it, the mineral is already locked in. Any later alteration risks destroying it. The Jadar Basin managed to thread this needle. In the end, jadarite is interesting not because it resembles kryptonite, but because it exposes how finely balanced Earth's geochemical systems really are. Given slightly different conditions, it would not exist. Given slightly different timing, it would have been replaced. And given slightly different tectonics, it would never have formed at all. This is why, 2 decades on, jadarite remains alone. A mineral that proves fiction can accidentally describe reality, and reality can still be stranger. Not because it glows, but because it formed once, survived, and quietly waited for humans to invent a reason to care. Economically, jadarite represents a paradox. It hosts lithium efficiently, yet it is not easily processed using traditional methods designed for pegmatites or brines. Its lithium is locked into a crystal lattice that must be chemically broken down, tying extraction directly to mineral processing rather than evaporation or simple crushing. This makes it both valuable and controversial. A mineral that challenges existing mining frameworks as much as it challenges geological expectations. What is often overlooked is how fragile that survival really is. Jadarite sits at the edge of stability, even today. Its crystal structure, with mixed boron coordination and incorporated hydroxyl, is inherently sensitive to changes in temperature, pressure, and fluid chemistry. Mild metamorphism would destroy it, acidic fluids would dissolve it. Even prolonged exposure to surface weathering would likely transform it into simpler borates and clays. The fact that jadarite persists at all tells us that the Jadar Basin experienced an unusually gentle geological afterlife. That is why, 2 decades on, jadarite remains alone. A mineral that proves fiction can accidentally describe reality, and reality can still be stranger. Not because it glows, but because it formed once, survived, and quietly waited for humans to invent a reason to care. I hope you found this as interesting as I did. And as always, thanks for watching. Before I end this video, I'd like to give a big shout out to my Patreon and YouTube members. Thank you so much to everyone that helps to support this channel.